All right, let's get right into it. Today, we are tackling something that trips up a ton of electronic students and hobbyists alike, the series parallel circuit. Yeah, they can look pretty gnarly, but I'm going to show you a strategy that makes solving them surprisingly straightforward. So take a look at this thing. It's a mess, right? A total maze of resistors and wires. It's really easy to just look at that and have no idea where to even start. But I promise you, by the time we're done here, you'll have a step-by-step method to solve not just this circuit, but pretty much any one like it. I absolutely love this quote from Jesse Mason because it's so perfect. This circuit really is the boss battle. And, you don't win a boss battle by just mashing buttons and hoping for the best. Nope, you win because you have a plan, you know the rules of the game, and you execute that strategy perfectly. And today, I'm going to give you that winning strategy. Okay, so before we charge in and fight the boss, we gotta check our inventory, right? We need to make sure we have the right gear. Every single circuit problem relies on a few really basic, fundamental ideas. So let's make sure our toolkit is ready to go. This right here, this is the absolute heart of the matter. If you can burn this into your brain, you are already halfway home. In a series circuit, everything's in one single line, so the current has only one path to follow. That means it's the same everywhere. In parallel, you've got separate branches, so the voltage across each of those branches has to be identical. Got it? Constant current for series, constant voltage for parallel. This is the key to everything.
And here are our 3 laws of physics for this universe. First, you've got Ohm's law, the classic V equals IR. It's our main calculator. Then you have Kirchhoff's 2 laws. His current law basically says that at any junction, whatever current flows in has to flow out. Electricity doesn't just vanish. And his voltage law says that if you go in a full circle, a closed loop, all the voltage you get from the battery has to get used up by the parts in the circuit. These 3 rules govern every single move we're about to make.
All right, toolkit is ready. Time to face the boss. Now, our strategy is a 2-phase attack. It's simple. First, we're going to break this complicated monster of a circuit down, piece by piece, until it's the simplest thing you've ever seen. And here he is. This is our challenge for today. We've got a 24-volt source, 4 resistors, all tangled up in that classic series parallel mix. And our mission, should we choose to accept it, is to find the voltage across and the current through every single component on that board. Now, trust me on this, staying organized is your best friend here. So we're going to use this table. It's like our score sheet. We'll track the voltage, current, and resistance for everything. As you can see, we start by just filling in the stuff we already know, the 24 volts from the battery and the value of each resistor. Everything else? Well, that's a puzzle we're about to solve. So, where do we start? The trick is to look for the easy wins. Scan the circuit and find these simplest little groups of resistors. We're looking for parts that are obviously clearly in series or in parallel. And right away, you can see R1 and R2 are hooked up across the exact same 2 points. That's a parallel pair. And hey, same thing for R3 and R4. Those are our first targets. Now, for the fun part. We replace those pairs with a single imaginary resistor that has the same total resistance. We just use the parallel resistance formula to crunch the numbers for the R1, R2 pair, and then do it again for R3, R4. And just like that, look how much simpler the circuit is already getting. And of course, we immediately update our table with these new equivalent resistors. We're adding columns for them to keep everything nice and tidy. This is going to help us trace our steps when we work backwards later. And would you look at that? After combining those parallel sections, all that complexity has just melted away. What we're left with is just 2 resistors connected one after the other. And that's just a basic series circuit. We can totally handle that. The final step of the breakdown is actually the easiest part. For resistors in series, you just add them up. So 71.429 plus 127.27 gives us one grand total resistance for the entire circuit, 198.70 ohms. And with that, we've broken down that complicated boss into one single, easy-to-manage part. Phase 1 is complete.
Boom.
Okay, we've successfully broken it all the way down. Now it's time for Phase 2. We build it back up. We're going to retrace our steps, working backwards from this super simple circuit, and as we go, we're going to fill in all those blanks for voltage and current. And this one little number right here, this is the master key that's going to unlock the whole thing. We have the total voltage, 24 volts. We have the total resistance, 198.70 ohms. So we can whip out Ohm's law and find the total current coming out of the battery. And that number is 120.78 milliamps. This is the key. So let's head back to our table and start putting this puzzle back together. We're going to use that total current number and work our way back up through the layers of our simplification. Now, remember that simple series circuit we made with our two equivalent resistor blocks? Well, since they're in series, that total current we just found has to flow through both of them. So we can just copy that 120.78 milliamps into the current row for our R1 for R2 block and for our R3/R4 block. See? The table's already starting to fill up. So now just look at those two columns for our equivalent blocks. For each one, we now know the resistance and we know the current flowing through it. You know what that means, right? It's time to call on our old friend Ohm's law again, but this time we're solving for the voltage drop across each of those chunks. Okay, this is where the magic really happens. We do the math and find the voltage across the first block is 8.63 volts, and across the second, it's 15.4 volts. Now, remember our fundamental rule? Voltage is constant across parallel components. So that means the voltage across the original R1 and the original R2 is 8.63 volts. And the voltage across R3 and R4 is 15.4 volts. We can just copy those values right into the columns for our original resistors. This is it. We are on the home stretch now, the final push. Look at our table. For every single one of our original 4 resistors, we now know its resistance value, and we know the exact voltage across it. All we have to do is use Ohm's law one last time on each of them to find the individual currents. And there it is. Victory. The boss is defeated. This is our original circuit, but now it's not a mystery anymore. It's completely solved. Every voltage, every current is known. We did it. We broke it down to its simplest form. We found that one master key, the total current, and then we built it all back up, unlocking every secret along the way. But wait, how can we be 100% sure we're right? In the world of electronics, you always check your work. A good engineer is always a little paranoid. So let's do one final check, just to prove that our method is rock solid. Now, you don't have to just take my word for it. Let's ask a computer. Here are the results from a SPICE simulation, which is an industry-standard program for this stuff. And as you can see, the computer's values for every single voltage and every single current, they match our numbers exactly. The method works, it's reliable, it's repeatable, and it's robust. So, we started with a boss-level circuit, and we beat it with a really simple 2-part strategy. Break it down, and then build it back up. This leaves me with just one final thought for you. This problem-solving technique, it's not just for circuits, so think about it. What other huge, complicated, seemingly impossible problems in your job, in your life, could you solve if you just found a way to break them down into smaller, simpler pieces first?